In 2019, Robert Geirhos and his colleagues showed ImageNet-trained classifiers images whose texture said one thing and whose shape said another, and the machines often followed texture where human observers followed shape. The common mistake is to treat successful visual similarity as understanding, when the choice of what counts as similar can separate a useful classifier from the way a category means anything to us. Geirhos and colleagues constructed Q-conflict images, pictures combining the shape of one object with the texture of another. A silhouette might present one kind of object, while its surface pattern suggested another. This was not a small technical curiosity. It made a hidden choice visible. When an image classifier assigns a label, which features is it treating as decisive? The standard ImageNet-trained convolutional neural networks in the study were more texture-biased than human observers. A convolutional neural network is a visual model trained to detect patterns in images. It could perform effectively on the task it had been given while relying on cues that diverge from human shape-based recognition. The researchers also changed the training material. They trained models on stylized ImageNet, and this increased shape bias. In the tested models, it also improved accuracy and robustness. Robustness here means maintaining performance when the visual conditions change in ways that might disrupt a more brittle cue. This matters because it gives us two ways to describe the same system. We can say it learned which images resemble its labeled examples, or we can say it learned to identify objects. The first statement is secure. The second carries more weight. It suggests that the machine has found something about what the object is, rather than merely something about how certain pictures tend to look. But there is a problem with this argument. Human recognition also depends on resemblance, and Ludwig Wittgenstein's account of resemblance begins by denying that categories need a single inner feature at all. The next question is, what sort of resemblance can hold a category together? Wittgenstein wrote Philosophical Investigations in the 1940s, and it was published after his death in 1953. In that work, he turns to a familiar category: games. The point is not that games are difficult to define because we have not yet found the correct definition. The point is that the demand itself may be misplaced. Consider the features that can appear in games. There can be competition, skill, amusement, rules, and luck. But these do not occur in one fixed combination. Some games involve competition, some foreground skill, some depend on luck, some are structured by explicit rules. No one feature has to appear in every case. Wittgenstein calls this family resemblance, overlapping similarities that connect members of a category without one property shared by them all. The image is not a hidden core surrounded by accidental variation. It is a network. One case resembles a second in one respect. The second resembles a third in another. Across the whole field there are crossings and continuities. This changes what it means to ask whether something belongs in a category. We may not need to locate an essence, a single property that is necessary and sufficient for every member. We may instead look at how similarities overlap within a practice of classification. That can sound surprisingly close to what an image classifier does. It too operates across patterns of similarity. It need not discover one eternal feature of cat or chair to assign labels. Yet Wittgenstein's point is not a theory of visual computation. He is challenging a philosophical picture. The picture that every meaningful category must rest on one fixed common property. The strongest objection, developed later by Daniel Osherson, Edward Smith, and Jerry Fodor, is that resemblance may not explain how concepts combine into new meanings. First, Rosch and Mervis will show how resemblance became an empirical model of categorization. In the 1970s, Eleanor Rosch's work on natural categories challenged the idea that everyday categories are defined only by fixed boundaries. Her research did not simply repeat Wittgenstein's observations. It brought a different question into view. If categories have internal variation, can that variation be measured in people's judgments? In 1975, Rosch and Carolyn Mervis published Family Resemblances, Studies in the Internal Structure of Categories. They found that some members of a category are judged more typical than others, and the typicality was related to family resemblance, the overlap among the attributes of category members. This is the basis of prototype theory. A prototype is a representative pattern around which judgments of typicality are organized. On this view, category membership is not always best pictured as passing through a hard boundary. Some cases sit closer to the representative pattern, others sit farther away. The shift is important. Wittgenstein had used games to challenge the hunt for necessary and sufficient features. Rosch and Mervis offered testable claims about category structure and graded judgments. They gave resemblance an empirical profile. We can ask which members people see as typical. We can investigate which attributes overlap. We can compare categories by their internal organization. This makes the connection to machine vision stronger. A classifier can also organize cases around recurring cues. It can locate patterns distributed across many examples, rather than searching for one universal visual mark. ImageNet training, in this broad sense, can look like a large-scale system for learning resemblance. But resemblance is not neutral. The attributes that recur may be texture, shape, or some combination. The Geirhos results show that a system can form an effective pattern of similarity while weighting the pattern differently from human observers. Rosch and Mervis help explain why categories can be graded and internally structured. They do not tell us which features ought to matter in every act of recognition. This is where attempting convergence needs to be resisted. Wittgenstein's family resemblances and Rosch's prototypes point in related directions, but visual AI exposes the difference between a philosophical warning and a psychological model. Wittgenstein does not offer, in philosophical investigations, a psychological mechanism for how people store categories or compute them. He does not say that the mind contains a prototype and measures each new case against it. His argument is directed against the assumption that a category must have one fixed inner essence. Rosch's prototype research does something more specific. It makes empirical claims about graded judgments and category structure. A prototype model can explain why some category members appear more typical than others. It can be tested against patterns in how people classify cases. That difference matters because a prototype model can classify by recurring cues, even when those cues are not central to what humans take the object to be. The model may have found a stable regularity. It may even be highly accurate, yet its regularity can still be texture when human recognition gives priority to shape. Geirhos and colleagues made this visible in 2019. Their results did not show that the classifiers were useless. They showed that the classifiers could be effective while relying on texture cues that diverged from human shape-based recognition. The model's success, therefore, does not settle what it has learned in the stronger sense. Wittgenstein helps here precisely because he does not hand us a computational recipe. Family resemblance does not mean that any set of recurring features automatically captures a category's meaning. It means that our demand for one hidden essence can be wrong. But rejecting essence does not mean accepting every similarity structure as equally adequate. A classifier can group images by a recurring pattern. Humans can also make graded judgments. Neither fact establishes that the classifier possesses concepts in the same sense, or that its categories carry the same role in use. The issue becomes sharper when categories are combined rather than merely recognized one at a time. That is the objection Osherson, Smith, and Fodor press through the strange but revealing case of the pet fish. In 1981, Daniel Osherson and Edward Smith published on the adequacy of prototype theory as a theory of concepts. Their target was simple prototype and fuzzy set accounts. A fuzzy set account treats membership as a matter of degree rather than an all-or-nothing boundary. Their objection was that resemblance-based accounts face a serious problem with conjunctions of concepts. Take pet fish. A typical pet fish can differ from a typical pet and from a typical fish considered separately. The combined category is not adequately explained by placing together the most typical features of each component. The conjunction has its own pattern. This matters because concepts do not only sort isolated items, they combine. When they do, the result can have a structure that is not simply inherited from the resemblance patterns of its parts. A theory that explains typicality within a category has not yet explained how the category contributes to larger meanings. Jerry Fodor made the broader criticism in Concepts, Where Cognitive Science Went Wrong, published in 1998. He argued that prototype theories do not adequately explain conceptual compositionality. Compositionality is the capacity of concepts to combine into meanings. The pet fish case gives that abstract problem a concrete form. This is the full force of the strongest objection. Similarity can explain why some examples feel central. It can explain graded judgments, but it struggles when a new concept emerges from a combination whose typical instance is not predictable from the typical instances of its parts. For visual AI, the lesson is not that pattern recognition has no value. Geirhos and colleagues showed that changing the patterns a classifier learns can improve tested accuracy and robustness. The lesson is narrower and more demanding. A useful similarity structure does not, by itself, explain conceptual meaning, and once a classifier's categories are attached to human labels, the question stops being only about texture, shape, and accuracy. It becomes a question about what kinds of classifications a dataset has made available in the first place. ImageNet was introduced in 2009 by Jia Deng and colleagues as a large-scale labeled image database organized with WordNet synsets. A synset is a grouped set of words associated with a concept. This organization made ImageNet enormously useful for training and evaluating image classifiers. It also made its labels part of the practical machinery through which systems learn to sort images. In 2019, Kate Crawford and Trevor Paglen released ImageNet Roulette, an artwork and research project that exposed harmful person labels in ImageNet-linked classification systems. The case changed the stakes of the philosophical question. A label is not merely a technical output when it is applied to a person. It can carry a category into a social setting where classification has consequences. Following criticism in 2019, ImageNet removed more than 600,000 images associated with person categories from its database. That action does not mean that all problems of classification were solved, but it demonstrates something concrete. The structure of a dataset, including its available labels and linked images, is not an invisible background detail. Wittgenstein's family resemblance argument offers a useful warning here. A category's practical use does not prove that it has a fixed inner essence. Categories can work through overlapping similarities. They can be sustained by patterns of use. But that does not make every deployed category natural, necessary, or innocent. ImageNet Roulette and texture bias reveal two different limits of the same easy conclusion. A classifier may rely on a visual similarity that differs from human recognition, and a classification system may inherit labels whose practical availability does not justify their application. In each case, successful sorting is weaker than understanding. The modern stake is not whether machines can find patterns. They clearly can. It is whether a pattern learned from labeled images tells us what a category means, which features should govern it, or when it should be used at all. When a classifier names a person or an object, what would count as evidence that it understands the category rather than merely reproduces a usable resemblance? Subscribe for more philosophy in concrete cases.